Class, welcome back. We are going to be finishing Whitlock and Schluter Chapter 10. I want to focus on the central limit theorem and a couple of examples as a result. This is the fundamental theorem of statistics. This is part of that fundamental structure that the Lord has put into the world such that there's this orderliness from which we can make many of the observations that we're going to make later on in this class. Without it, things wouldn't work. Now, briefly, it says that sample means are normally distributed, and it gives the mean and the standard error for the distribution. What I'd like to start off with is illustrating this using software. Now, let's consider rolling a single six-sided die. Okay, and I'm going to do that 10 times. We're going to roll that die 10 times, and we're going to collect those results and put them in a histogram. Okay, as you can see, we got 3 1s, we got 1 2, 1 3, 3 4s, no 5s. Okay, 2 6s. Now, if I were to shake that die and do it again, what would happen? Well, here's a possibility. Here's another possibility, and I'm just going to rattle through several possibilities. You can see that on average, we keep getting things to spread around. We didn't get any more than 4. It's possible to do that. It would be rare. Often had gaps. What if we didn't do 10 dice? Let's just kick it up to 100 dice. Let's do a comparison. Oh. No gaps this time. There's somewhat of a gap, but still had 10 of them on the 2s. Similar with the 2s. Having trouble getting 2s here. Looks better. More rectangular shaped, which is the theoretical ideal, 1/6 of each, but it's not quite there. Let's kick it up to 1,000. And now what do we see? Not too bad. Not too bad. Okay, so that's what we get with this single die rolled multiple times. That is not the central limit theorem. That's the law of large numbers. The law of large numbers says that the empirical probability distribution is going to approach the theoretical, and that's what we're seeing. Now, what's the central limit theorem again? It says the mean goes normal. What do you mean by that? Okay, what we're going to do now is, remember when we were rolling those 10 dice? This is the file that we're in right here. And I'm just grabbing this command. We'll run it. Run that guy. I'm going to change my n back to 10. We're going to roll 10 dice. But this time, what we're going to do is we're going to roll 10 dice, and then we're going to take the mean. And then you can think of each student in the class all rolling 10 dice and all giving me their mean, along with some other students. We'll have 1,000 students to do this, and we'll plot those 1,000 means into a graph. And this is what happened. If I didn't take the means, I just took all the dice, 10 per student times 1,000 students, 10,000 dice, this is what I would get. See the law of large numbers kicking in. But these are the means. Now, the central limit theorem says that the distribution of those means is going to approach the normal distribution, or it is approximately normal. Taking a look, we're getting that same mound-shaped distribution every time, and it turns out that that shape, if you check the percentages, is about the normal distribution. What I want to do now is kick it up. Instead of 10, let's just use 100 dice per sample. Computer's blitzing out here a little bit. Okay, using 100, and I've got a lot of applications on. But if we're keeping our eye focused on this distribution, we're seeing that it changes, but not much. Okay? And lastly, let's go ahead and kick it up to n equals 1,000 dice per roll. Now this will take a little while to run. That's 1,000 times 1,000. That's 1,000,000 observations that are going to be considered. Notice the law of large numbers, it's pretty flat, and that looks pretty good. What changed? I'm just going to use my little back arrow here. That was a 100, 100, 100, 100, and this is the 10. Notice the x-axis down here. When I switched from the 10 to the 100, it got smaller. That is, the standard deviation shrunk. And when we kicked it up to the 1,000 case, it shrunk again. That is the same shape of the normal. The mean stayed the same throughout. Notice it's always about 3.5. And the standard deviation shrunk. So with that, let's go it here. Okay. Mean is equal to the parent mean. Standard deviation is equal to sigma over rad n. So, diagram. I like to consider that we have some random variable x, doesn't matter what it is, that's my population, and then I'm taking out samples. There is a true population mean, but in the sample I only get an x bar. My x doesn't matter what its shape is. In fact, let's make it not normal. We had an x that happened to be uniform, so let's just say that's x. This is the parent distribution. Now the child of this distribution, when I look at its means, it goes to a normal, x bar. This is the child. And we saw that in the distribution. So this parent here has a true mean of 3.5. This child distribution will have the same mean as the parent. And furthermore, this parent distribution has a standard deviation of sigma. The child has a standard deviation of sigma over the square root of n. It shrinks according to the sample size in our sample, and that's remarkable. Now, according to the theorem, it says that we're approximately equal to. That little circle over the equals, the distribution follows sign gives us approximately. How big does n have to be until the approximation is good? Traditionally, 30 has been a number considered good enough. Okay. We'll keep that number in mind for this class, and I'll comment more on that number later. Okay. I would also like to point out that when the parent is actually normal, then the approximation goes away. The result is exact. So that's something to keep in mind. Remark number 3. We have a standard deviation of the parent, and then we have a standard deviation of the child. In order to distinguish these two, we're going to keep the parent called standard deviation, but we're going to call the child's value standard error in order to make that distinction. So the standard error of the mean of x bar is the standard deviation of the parent divided by square root of n. However, this is the standard deviation of the distribution of means. It's simply named so as to give us a distinction. What else do we have? That covers 1, 2, 3. Demonstration using R, we did. I'd like to do a couple of exercises and close it. First exercise. Want to revisit the Canadian systolic blood pressure data that we did in the last segment, okay? We have mean 121, standard deviation 16, and let's suppose we get a sample of 30 measurements. Last time we asked, what's the probability that an individual has high blood pressure? And when we did that, what did we get? Let's see. There it was about 11-12%. Now, what's the probability that the sample mean, that is an average of 30 people, has high blood pressure? What does your intuition tell you? Should it be larger? Should it be smaller? We're going to consider this. Okay, so first of all, we're going to say since n is over 30, we'll go ahead and use our central limit theorem. We should have mean 121. Standard error is going to be 16 over square root 30, which is 2.9212. It's a good idea to use 4 decimal places for standard errors. It doesn't matter so much here, but it will come in. Now, for the z-score, we have stat minus parameter over standard error. That's the same formula we had before, and this formula will be with us all semester long. But the statistic, instead of being x, is x bar. The parameter is still mean. The standard error is sigma over rad n. Okay? So, x bar, we're going to use 140, mean 121, standard error 2.92, and we get 6.5. Whoa! Okay, the alarm bells are going off. 121 to 140. It's way out here on the flaming right. 6.5. We know that that's almost nothing. And if we go to the table to confirm, then we're going to see 6.5. We're off the chart. Okay, so we will use 0.00001 for values past 4. Okay, so let's go ahead and put that 0.00001. Okay, so we'll put, we should put a 0.01% chance, 0.001% probability that this would happen. Virtually impossible. Okay, last example here. Coal cars. All right, last time we had the probability of a single coal car getting a half a ton short. This time we're talking about 40 coal cars averaging a half a ton short. Sample size is 40 coal cars, so our normal approximation is justified. Central limit theorem should kick in. So means of size 40 from the sample. In theory, they should have a mean of 75 with standard error 0.8 over square root of 40, which is 0.1265. Okay, so sketching the curve, we're going to have a mean of 75, and we're down here at 74.5. We know it's kind of low. How low? We want less, so I'm going to shade on the less side. Okay, let's do the z-score on the side. Z equals 74.5 minus the mean 75 divided by the 0.1265 standard error. And that's going to give us minus 3.95. So this is probability z less than minus 3.95 is. Now I'm on the left-hand side, so on the table read, I'm going to take the positive and read the right side. That's symmetric to the left. So 0, 1, 2, 3, 4, 5. There's 4 zeros and a 4. Okay, so 0.0004. 4 zeros and a 4. Okay, so we have a 0.004% chance of this occurring. Almost impossible. So we're going to have to question that manufacturer's claim and act accordingly.